Now, if you submit that to, if you shine light on that, what you have done is you will then generate an electron-hole pair, and because of the asymmetry and the concurrent field that is produced, the charges will separate. And they will be collected as photocurrent. The photocurrent is always represented as being a positive current. Remember, there's all these problems with physicists and chemists and directions of current scope. But remember that in a solar cell, the photocurrent is a positive current. Now, this is an expression for the short circuit current density that you can get out of that cell. Now, there are two things that are important about this particular equation. One is this function, Bs of E, which is basically what is the light density, the spectral photon flux density coming into the cell. Now that matters. It matters whether you're on the ground. There's one solar spectrum. There's another solar spectrum if you're up in space, outside of the Earth's atmosphere. We call that air mass 0, meaning there is no air between you and the sun. Normally, when we calibrate standard solar cells, we calibrate them at air mass 1.5, because unless you live on the equator, the sun is never really right over your head. It's off here somewhere in the sky. And in fact, in Cleveland, it's 41 degrees, actually, above the horizon. The other part of this equation is the quantum efficiency of the cell. All of these are a function of energy and then integrated over the energy spectrum. The quantum efficiency relates to the device itself. It represents how well does the material absorb light, how well do we separate the charges, how well do we actually collect them. Now, there's a lot of physics that goes into those parameters. We won't go into the details today, but I wanted to at least do a few critical things. Is it going to? Yes, it will go. And at least give you a sort of general knowledge. If you think back, some of you may have had solid state physics where you look at solid materials. You can take one atom and it can have an energy structure. If you take two atoms, you will find there is a splitting of energies. If you take three, there are more splitting. If you take n number of atoms in a solid, you have what we refer to as a band characteristic for a semiconductor. Here you represent the valence band and the conduction band. And for a simple device that's pictured above. These are the minority carrier densities for the whole, the positive, if you will, part of the current, and the electrons. Now, there are all kinds of things in this, including things like what is the range of the interaction, what is the width of the region as we separate the charges, and that's called the depletion region. The idea being you sweep the charges out of that region. Remember that because that's a very sensitive region for a solar cell. If you want to make it die, put some impurity in the depletion region, and it dies very nicely for you. These constants, FP1 and FP2, relate to the things like the recombination velocity of the carriers in the bulk material and on the surface, the diffusion length of the carriers, and a variety of other things. The Fermi energy, by the way, for those of you who haven't gotten so far as solid-state physics, is the level at which, at absolute zero, all of the energy bands below it are filled and all the energy bands above it are empty. Now, we're not going to operate at absolute zero, and so life gets a good deal more complicated in an actual solar cell. And this is a very simplified version that you can use to identify the basic parameters that are of interest here. One is the open circuit voltage. That's as if you had the light generating capability and you disconnected the load from the circuit. The other is the short circuit current. So this is the open circuit voltage right here, okay, when the current is zero. And this is the short circuit current maximum. That's when you have the ends of the device shorted out, so you get the maximum amount of current. The ratio of the area, if you're operating at some power, perhaps your max power point, that's what the MP stands for, the ratio of that area, the blue part, relative to the red part, is what is called the fill factor of a cell. Now, if it were an ideal cell, it would be 1. Nothing is ideal. The efficiency, quite simply, is the ratio of the power density on the surface of the cell relative to the power density of the electrical output of the cell. So it's how well you actually convert the sunlight into usable electric energy. Now, it does depend on how bright the light is. And you can well imagine why that's the case, because if you have more photons, you'll generate more carriers. What's interesting about the solar cell is, though, that's almost entirely an effect of the current. You'll see very little change in the voltage as you go, and in the middle is one sun. By one sun, what we mean is the amount of sunlight at the radius of the Earth from the sun. Okay? When you go to two suns or 5 suns, you are concentrating the light. When you're going away from the sun, such as if you were to go to distant planets, you are now diminishing the intensity of the light. And what you can see is, of course, that it is the current that changes predominantly. Another effect and this is what we measure for some real cells, by the way. One of the things you can see here is that if you look at high intensity, high temperatures, the wider band gap materials do better. And there's some logic to that if you look into all the mechanisms that produces the current for a cell. Likewise, since we do take missions into the sun. Messenger just finished a mission into the sun. We also take, at some radius from the sun. We also go out to the planets where not only is the intensity low, but the temperature is low as well. And you'll see that some materials, such as silicon here, do not necessarily do very well under those conditions. So this is a picture separated out of what temperature actually does to a cell. If the temperature increases, you get a higher current. That's the red, but a slightly lower voltage. If the temperature decreases, the current decreases, but the voltage increases. So those are how, and in general, you lose more with the voltage than you do with the current. This is a comparison for you of those two spectra I talked about. This is what it looks like in outer space at the Earth's orbit. And this is what it looks like on the ground.